Hi, I'm Professor Goines, and welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in just about any college mathematics course, please consider subscribing, checking out our playlist, watching videos, liking, commenting, sharing those videos. Those are really simple interactions that you could do that would help us to grow, and we would greatly appreciate it. Let's get into the current video. I want to take a look at the concept of compactness in a topological course. Okay, so what do we mean by compactness? Now, one sort of intuitive idea might be like, well, if it's compact, so again, let's think about maybe in the real line. Compact maybe is like bounded, something like that. Well, if I look at again, the real line with the usual topology, okay, and let's consider the open interval 0 to 1. That's clearly bounded. And could that be compact? Well, keep in mind the open interval from 0 to 1 is actually homeomorphic to the entire real line, which is not bounded. So in particular, boundedness is not a topological property. Now, of course, in metric spaces, we can consider the concept of boundedness, but in a general topological sense, without a metric, boundedness is meaningless. But in particular, it's not even a topological property. So within this topological space, those two are homeomorphic. One is bounded, one is not. Clearly, then, that's not what we necessarily mean. Or perhaps there's a little bit more to it. Not just bounded, but maybe there's something else we have to add to it. Well, the concept of compactness is less intuitive than something like connectedness. It's not as geometric as the concept of connectedness is. And the way that we have to approach this idea is we have to do it through a handful of definitions. And these definitions, again, are not necessarily intuitive, but they are fairly workable. So I'm going to go ahead and give a variety of definitions here. In a topological space x tau, an open cover is a set A, which is contained in the topology. So it's an open cover is a collection of open sets for which if I take the union of every element of this collection, okay, so I take the union of everything in this open set A, or this collection of open sets A, I get all of X. Or let's say in general, it contains X, in case we're talking about subspaces or something. But it will contain all of X. So it completely covers the space, right? The union of all the open sets is basically kind of like a patchwork, and it's kind of cover the entire space. An open subcover of A is a set B, which is contained in A, where the union of all the elements of B also contains X. Said differently, it's a subcollection of the open cover, which is also a cover itself. Okay? So that's what we mean by an open subcover. Now, let's take a look at what we mean by an open cover. All right? Let's take R with the usual topology. So we have a concrete example of an open cover. Let's say my set A consists of the open intervals n to n plus 2 such that n is any integer. By the way, that's supposed to be a script z. Let me do that. That looks a little messy there. Well, this right here would be an open cover because if I take the entire real line, let's say I go, so 0, 1, 2, 3, 4, etc., -1, -2, etc. What I'm doing is I'm taking the following open sets. 0 to 2, okay, so there's 1, and then I've got 1 to 3, and then I've got 2 to 4, and so on and so forth. So if I take the union of all of those, it does actually provide a complete cover for the entire real line. And notice that I cannot actually take any of these open sets away and still have a cover. Therefore, this open subcover that I just created does not have a subcover. Okay, let's take a look at some more examples. Actually, let's take a look at the definition of compactness first. All right, here's the definition of compactness. So definition. Okay. Topological space X tau is compact if for every open cover A of X, there exists a finite open subcover. Of A. In order for a topological space to be compact, if I could take any open cover, I can extract finitely many of those and still have an open cover. You could then see that the entire real line in my previous example is not compact. And that was kind of intuitive, sort of, because we, at the very beginning, were like, well, compactness should at least involve some sort of a concept of boundedness, even though general topological space boundedness doesn't make sense, at least in the sense of the context of the real line. Compactness should somehow involve boundedness. And we saw that the entire real line was homeomorphic to 0 to 1, which is an open bounded set, which isn't therefore compact because the entire real line is not. Okay. Well, what I'm actually saying is compactness is a topological property, and that's the next thing that I'm going to prove, is that if I have a continuous function from a compact space to another space, its image, and what I'll do, just to kind of make the notation a little bit cleaner, is I'm just going to assume that it's a surjection, or it's always surjective onto its image, but I'll say that it's a surjection, and therefore the target space will be compact as well. So let's go ahead and prove that. So proposition. If F, which is a mapping from X to Y, is a continuous surjection. Again, so that means it's a continuous function, and that means that the image of the domain space is the entire target space. So it is a continuous surjection, and X is compact, then Y is compact. Okay? Let's prove it. Well, what I have to do is let's use the definition that I just wrote. I have to be able to choose any open subcover of Y and show that it has a finite subcover. Well, let's start by choosing an open cover of Y. All right, so let A be an open cover of Y, so that, and I'll basically just write out what that means. If I take the union of every element over that set A, this is going to contain, in particular it's going to equal, but it's going to contain y. Okay? It's also going to equal y because y is the entire space. Well, then this also gives me that x is equal to, of course, the preimage of the entire space y, right? Remember that F was a surjection. And this would also be equal to the preimage of the union of all of those sets. Okay? So F is equal to, or the preimage of the union is, of course, the preimage of y, which is all of x because this is a surjection. And by continuity, since all of these sets A are open, the preimage of A is open in X for every, of course, A within that collection. And hence, the set of all preimage of A, such that A is an A, is an open cover of X. Well, X is compact. So by compactness of X, this has a finite subcover. The corresponding A's, so if I take the preimage of, say, A1, the preimage of A2, preimage of A3, whatever that finite list is, I take all those sets A, give a finite subcover of the original set A. Well, that's exactly what it means to be compact. Is if I take any open cover, I can find a finite subcover. And that's what we just did. Therefore, the target space Y is in fact compact. And this right here is one of the most important properties, or at least propositions, related to compactness, because it does prove that compactness is a topological property. It's preserved by continuous functions. In particular, if I have a homeomorphism and X is compact, we know that Y is compact because we just proved that. But on the other hand, if F is a homeomorphism and Y is compact, then I also know that the domain space is compact as well. Again, it's a topological property. Right? Okay. The extreme value theorem. And as soon as I wrote that, I realized there was something that I did not state yet that I'm going to need throughout that proof. So let me go ahead, and I'm not going to have the time to prove this right here, but here's another proposition before I get to the extreme value theorem. At the very beginning, I mentioned within the context of the real line, compactness should somehow involve boundedness, and it does, but there's one extra thing we have to do. I'm just going to say in Rn, and I'm going to assume that it's the usual topology, so whether that's the real line or the plane or three space, etc., compactness is equivalent to closed and bounded. Okay. Therefore, in the real line, on the real line, again with the usual topology, the closed bounded interval 0 to 1 is compact, whereas this Open interval is not compact. So closed and bounded is equivalent to compactness in our typical Euclidean spaces. Now let's prove the extreme value theorem. And of course, the extreme value theorem is something that you should be familiar with from your calculus course. I'm going to prove this in a slightly more general setting, and I'm going to say that X is a compact topological space, and F is a mapping from X to the real line, is continuous, then F attains both its maximum and its minimum. Now, of course, in the context of a calculus course, your domain space is going to be a closed bounded interval, hence compact. And remember, if I have a function from, say, like the closed interval from 0 to 2 to the real line, or it's just a function on that closed bounded interval, it's going to have both its maximum and its minimum. But I'm just going to state this in a slightly more general context where the domain is simply a compact topological space. It doesn't have to be a subset of the real line. Let's prove that. Okay. And I'm going to use the previous two propositions. Well, if X is compact and F is continuous, then F of X, which of course is a subset of R, right, because F is a function in mapping into R, then F of X, the image of that compact space, is compact. Right? So F of X is compact. Compact in the real line means we have F of X is closed and bounded. Well, if a set is closed and bounded, then F of X, so that set F of X contains both its infimum and supremum. That means the absolute maximum function value that you can get from F is actually an element of the target here, F of X, or the image. Same thing with the absolute, maximum, absolute minimum, and absolute maximum. In other words, the infimum and supremum of the set are in that set, and therefore the function does attain both its maximum and its minimum. Okay, thank you for watching, and please consider subscribing.